In this video session, we are going to talk about a very important device that is used in instrumentation that is called a wheatstone bridge. Okay, this is a very important instrument that is used for actually converting the sensor value into electrical signal, right? So this you must have also studied earlier in your preliminary classes, and I think this diagram looks very much similar to you all. Wheatstone bridge is actually a electronic device, you can say, or it's a kind of a circuit in which you have four resistances attached as four arms of the bridge, as you can see in the figure. And under perfect balance conditions, there is no current flowing in the center. The center branch, and so if r1 is equal to r2 and r3 is equal r1 upon r2 is equal to r3 upon r4, then it is called a balanced wheatstone bridge, and there is no current flowing in the central branch. Okay, so this is the most commonly used DC bridge for the measurement of resistance. This bridge is used for measurement of small resistance changes that occur in passive resistive transducers like thermistors, strain gauges, resistance thermometers, etc. So what happens is, whenever you have a transducer which is working in terms of resistance like a strain gauge, that we attach in one of the arms, usually at place R1. Okay, so at R1, what we do is we place a strain gauge. Okay, and rest of the arms are balanced in such a way that it shows zero deflection. That means there is no current flowing in the center branch, right? So when there is a change in the any physical phenomena, like for example, strain gauge we use for change in geometry or pressure, like that. So whenever there is a change in any in that particular physical quantity, the resistance of my sensor changes. So that means resistance of that particular branch will change, and it will cause an imbalance in my bridge. So, right. So now this imbalance we can deal in two ways. One is that I make a corresponding change in another arm and bring the deflection back to zero, right? So and then I measure that how much change I had to introduce in the other arm to bring it back to zero. Or the other thing could be that I simply measure how much deflection the galvanometer is showing in the center, and I calibrate that deflection to the change in resistance, right? So on the basis of these two types of variations, we can divide the working of a wheatstone bridge as null type or deflection type, right? So in null type, what we do is we, under balance conditions, we know that R1 upon R2 is equal to R3 upon R4. Right now, R1 over here is representing the resistive transducer. Right. So what we do is, whenever there is a change in the physical parameter, the resistance R1 changes to R1 plus delta R1. Okay, now this creates a imbalance. Now in null type, what we do is we purposely introduce another change in the resistance to balance the condition. So what I have to do is, if R changes to R1 plus delta R1, if I have to balance the bridge again, I have to introduce a corresponding change in R2, so that the arms they balance and the deflection comes to null. So what I do is I introduce a change R2 plus delta R2, right? In the resistance arm R2. So now what happens in the new balance condition, what I get is R1 plus delta R1 is equal to R2 plus delta R2 into R3 by R4. Now when I calculate I calculate this, I can calculate the delta R2 in terms of delta R1 R4 upon R3. R4 and R3 are constant resistance values that I know. Delta R2 is actually the known resistance change that I have introduced into the circuit. So when I place all these values, I can calculate the value delta R1. This delta R1 was actually the change in the resistance that occurred in that particular transducer, corresponding to the change in the physical parameters. So if the pressure changes, strain gauge resistance changes, it changes from R1 to delta R1. So what I do is delta R2 is intentionally introduced into the circuit to bring it to null. Okay, bring the deflection to null, that is zero deflection. And then for using this formula, delta R2 is equal to delta R1 into R4 upon R3. I calculate delta R1, that is a change in resistance that occurred in that strain gauge, and that change is actually again calibrated in terms of pressure that we actually wanted to measure. So this is one method in which the null type functioning can be performed in a wheatstone bridge. Now this whole thing, instead of doing it manually, you can actually automate this whole thing by introducing a motor. What happens is this when there is an imbalance taking place in the branch in between this point B and point D, some current will flow. What I do is, instead of putting a galvanometer over here, that current I supply with the help of an amplifier to a motor. Now, when this current is supplied to the motor starts functioning. The rotation of this motor will actually take place proportional to the voltage that is applied. And this motor is actually mechanically coupled to the scale or a tap over here at R2. So what will happen is, this current, it starts the motor. This motor moves the position of the scale in such a way that this R1 and R2, they get balanced. When this pointer comes to such a point that these two arms, they get balanced, so there the current coming from point D will automatically become zero. That is, null point will come. Null deflection situation will be achieved over here. So as soon as this current actually stops coming to the motor, the motor will stop and there will be no further change in this scale. So instead of manually introducing that change, I can put a DC motor over there, supply the current to the DC motor. The DC motor will change the variable resistance tap will be changed, and you can actually attach a scale to it, which will automatically show you that by how much amount the value R2 has been changed to bring this circuit back into the null deflection situation. Okay, then for corresponding to that, you can directly put that delta R2 into the equation and calculate delta R1. Instead of manually adjusting, you can use a DC motor to actually do that automatically. Okay, now this kind of a configuration of the Wheatstone bridge is good if your values are changing slowly, or you can say that if it is a low frequency data. But if your data or if your value of the sensor is varying very dynamically, then because of the mechanical movements that are involved in the resistance movements, etc., because of the inertia involved, the Wheatstone bridge actually does not respond very quickly for dynamic responses. In that case, we use deflection type. In deflection type, what we do is that we simply see that whenever there is a change in resistance R1, there will be some current flowing through the galvanometer, there will be some deflection taking place. That deflection we observe, and we calibrate the deflection in terms of resistance, and resistance further in terms of pressure or temperature, whatever is the physical quantity. Right. So what in this case, what happens? There is no mechanical movement taking place. There is no the response speed is very fast in case of deflection type. Simply because of the current, there will be a deflection taking place, and we simply have to note down that deflection. Okay, and that deflection can actually, if you want to improve the circuit further, that deflection can be fed to a display device where you can establish a calibration between that voltage deflection or a current deflection in terms of maybe pressure or temperature, whatever the physical quantity that you were measuring was. Okay, so Wheatstone bridge is actually the most popular device that we use to convert the resistance into a corresponding electrical voltage or a current signal. Okay, we can use it either in null type or in deflection type. Null type is used when it is a low changing data or a slow response is required, and deflection type is mostly used where the data or the input is actually changing very rapidly and a very fast or a very dynamic response is required.